Hello everyone, welcome back to Fundamentals of Nano and Quantum Photonics. So this is the week 11 of the course. So in the last week we were looking at how to treat quantum light. I mean we introduced these ideas of quadratures and we introduced what are known as coherent states, and towards the end I think I rushed through what we call as squeeze states. Okay. So in this week I just want to first talk about a little bit more about squeeze states. We'll give you a more intuitive picture, and then we will talk about what are known as photon number states. So these are essentially the common terms that you will encounter in the domain of quantum photonics. So we want to introduce. Okay, so let's get started. So this is something that I have shown you in the last week. Towards the end, the last 10-15 minutes, I showed you what are the squeeze states. So let's discuss them in a little bit more of a detail. Okay. So first of all, any questions from last time? Yeah. So the question was, we understand how a classical harmonic oscillator behaves, right? We have position and momentum. We talked about it right in the beginning of the last week. But how do we visualize what it means when you show this, let's say, coherent state on a quadrature plot like this, x1 and x2, right? What does it mean? So to understand that, one thing we have to remember is what are these quadratures, x1 and x2. If you look back at the definition that we gave last week, let me try to find that. So, yeah, here. Or rather, this is better. Yeah, here. So, the x1 quadrature is essentially defined in terms of sine omega t, and it is related to the generalized position. And x2 is basically defined as cos omega t, and it's related to the generalized momentum. So you see that these are out of phase. One is sine, one is cosine. So they are quadrature, right? They are in quadrature. So now, basically, let's say this x1, I'll mention it explicitly here. X1 is proportional to, let's say, q. X2 is proportional to p of t. Let's say q of t. So in a classical picture, let's say if you consider a classical harmonic oscillator, how would you represent that? Okay. The important thing to realize is that, let's say we talked about x equal to x naught cos omega t, I think. Cos omega t, p is equal to p naught sin omega t. These were the two variables that we can use to describe a harmonic oscillator, correct? So now, at any point, I'll have an x and p, and then I can represent that in this plot. Okay, let's say I have a point here. This is my position. Let's say this is where my harmonic oscillator is right now. Now, how does it evolve in time? Okay. Or I can take an extreme scenario. Instead of putting it in the middle of the graph here, I'll put it only on the, let's say, on the axis here. Okay. That tells me that this mass spring system harmonic oscillator is at position some x naught here at time t equal to 0. Now, as time evolves, what happens? So x naught means, let's say the pendulum is at the extreme. Okay. Now with time, it will come back and go to the other side, correct? And then go back and forth. So if you wait for 1/4 of the oscillation period, then you will find that this point would actually, the x naught will come down to from the extreme, the pendulum will come to the center, where the velocity will be maximum, but the position is 0. So in effect, this point on this quadrature plot would have moved here, correct? So essentially in 1/4 of the period it will go here, in half the period it will come here, where x will become minus x naught, and the momentum is again 0 in the other extreme, correct? Again goes back and forth. So effectively your harmonic oscillator can be represented by a circle on the x1 x2 plane. Okay. So like if I want, instead of this, I draw my instead of x1 x2, I'll call it q and p. Okay. In such a scenario, my classical harmonic oscillator is represented with a circle. Okay. Okay. So classical harmonic oscillator. So basically this plot between these two quantities in quadrature represents the motion of the harmonic oscillator. Okay. Now when we come to light, why did we get to the point, x1 and x2? Okay, why did we introduce this quantity, quadrature x1, quadrature x2? The reason we did that was, you see, the position and momentum have completely different units, correct? So position, let's say, is few centimeters. Momentum is going to be some velocity times 10 power minus 31. So it's a very, very large mismatch in the dimensions. Because of that, if you represent on such a plot, it will be very inconvenient. Ideally, if you just call it x and q and p here, this will most likely, it will be like a very stretched out thing. It will not be ideally, it's some sort of a closed form. It just represents. Maybe I'm actually probably, wrong in saying that it's a circle. It will be something like this, right? So you will not even see it. It just moves on this. If you don't plot it without proper normalizations. So that's why instead of actually plotting in P and Q or generalized coordinates, we define these dimensionless quantities. When we define in dimensionless quantities, it will definitely be a circle oscillator in dimensionless units, right? If I don't use dimensionless units, then it will be very stretched out ellipse. Okay, that's not convenient. So that's why we represent. Okay, so now instead of that, let me correct that and say that this is instead of this is x1 and x2 now. I represented using dimensionless units. Okay, now what is the difference from that and the electromagnetic wave? We said electromagnetic wave also is a harmonic oscillator. Okay, the only difference comes about, we said, is because of the uncertainty principle. So we cannot exactly know what is my amplitude, and the q and p, right? So x1 and x2 cannot be exactly determined, and they have this uncertainty in terms of x1, delta x1 is half and delta x2 is half. The product of uncertainties is basically the uncertainty relation. Just like we had in the classical case between position and momentum, we have an uncertainty relation. Even between x1 and x2, we have an uncertainty relation. So the area of minimum area is basically determined by the uncertainty principle. Minimum area is determined by uncertainty. Delta x1, delta x2 equal to half. Okay, so that's a region of uncertainty. All right. Now this is a coherent state. Okay, so that means now I can't talk of a single sine wave, but I have to take a combination of sine waves. I'll just go into a little bit more detail in the next slide. Okay, but from here, how do we get to a squeeze state? Okay, what does it mean by a squeeze state? So in the case of a classical harmonic oscillator also, let's say you are having a mass suspended by a string. It turns out that if you drive it parametrically, that means, okay, you apply a periodic modulation to the length. Let's say this is one of the cases. It turns out that the amplitude gets very strongly amplified. So the wave, the pendulum oscillates very, very in a very large degree, and then the momentum actually becomes the variation in the momentum becomes very small. That is what is classically it can be shown. We don't want to get into all that, but essentially the key result is that if you drive the pendulum at twice its frequency, twice its natural frequency, the position gets exponentially amplified and the momentum gets attenuated. So effectively in your quadrature plot, this becomes like this. Okay, so essentially the momentum is getting squeezed, it's getting exponentially decreased, but the position becomes exponentially bigger. Okay, so this is basically a momentum squeezed state. Sorry, the black one is a momentum squeezed oscillator. It can happen only when you have, let's say, certain conditions like you drive it. If you take a case of an LC resonator, the capacitance of it you change at twice the resonant frequency somehow. We always study fixed L and C. But suppose you are able to have a time varying capacitor that is getting modulated by twice the resonant frequency, what will happen? So some of these things can actually be studied. It turns out that you can actually do this. Okay. Similarly, in the case of quantum sources, we said this is the x1 quadrature and the x2 quadrature. So what do we call this state on the left here? Is it a coherent state or a vacuum state? Vacuum state I will call it, because the number of photons is 0. Why do I say number of photons is 0? Because it is at the center. and the size is basically half and half. So the product is minimum uncertainty. That's a coherent vacuum state, maybe we should call it. Okay. So if you had to represent another state which has, let's say, 5 photons, then I would have to represent like this, right? This is my distance. This will be square root of 5, correct? And this is my state with 5 photons and so on. Well, actually, okay, 500 photons I should say. Large number of photons. Then you can represent this. Okay. So basically that is your normal state, coherent state. But then we can actually try to squeeze it. There's nothing that forces us to have uncertainty relation, region of uncertainty as a circle. As long as you make the area greater than 1/4 in dimensionless units, you can have different shapes. So for example, instead of a circle, I can have an ellipse like this, or another ellipse in this perpendicular direction. There's nothing that stops us. And these essentially, what does it mean? It means that this the way this x1 and x2 are effectively position and momentum in the or electric field, or also related to electric fields. We have seen that. So now the way the fields are changing is getting changed. Basically, when the shape changes, the way the fields respond with time changes. Okay. So how do we do that? So basically we introduced these quantities last time. I'm just refreshing it and I want to elaborate on it. That's why I'm doing this. So the first scenario is your regular quadrature squeeze states, right? Correct. So what do I have? Just one moment. Okay. Yeah. So if I have the left, so this is my coherent state. So my delta n is going to be square root of the average photon number, and the uncertainty relation holds. I mean, what are the uncertainty relations? Delta x1, delta x2 should be greater than 1/4, greater than or equal to, and delta n, delta phi should be greater than half, right? These are the uncertainty relations. Now what we are saying is, of course, instead of along the axis, I am actually stretching the region of uncertainty along the radial axis and compressing it along the phi angle, whatever, the azimuthal angle. Along that we are trying to compress it. Okay. So now what will happen in this case? We talked about the uncertainty relations, right, in the number and phase. So we said that if you have a photon like this, there has this uncertainty relation. Now if I am stretching it along the radial axis, I am increasing uncertainty in number of photons, n bar, correct? Delta n I'm increasing, right? So increasing delta n, right? That's uncertainty in n bar. Now if I increase uncertainty in n bar, of course, I'm also reducing delta phi. That's what this ellipse means. So basically this we call it, since we are reducing the uncertainty in the phase, I'm calling it phase squeezed light. Phase squeezed light. Is it okay? So the question is, what will happen to the statistics? What sort of statistics will the phase squeezed light exhibit? Okay. Now we are reducing. If we talk about just simply Poissonian, the number statistics, delta n is in this case going to be greater than square root of n bar or less than square root of n bar? Yeah. So if you have a coherent state, delta n is going to be square root of n bar. But now we have increased uncertainty because along the radial direction we have stretched it. So delta n, that's the fluctuations in the photon number, is going to be greater than square root of n bar. So what sort of statistics is this? Super Poissonian. Right. Now we can also think of another scenario wherein you actually stretch it in the angular direction, okay, and in the radial direction you compress it. Okay, instead of in a circle as a region of uncertainty, I have an ellipse now, but the axis of ellipse is different. So in this case now, since my photon number corresponds to the amplitude of the electric field, right? Because that's what we said. So this we call it as amplitude squeezed state. Squeezed state. And what are the statistics for this? What will be the delta n? Now delta n is actually less than the coherent state. So basically delta n is less than square root of n bar. So this will be sub-Poissonian. Alright. So this is how statistics behaves. Alright. So any questions? Well, I have one question. So what happens to the phase? We are saying that phase is more, delta phi is more than Poisson case or less than Poisson case. But it turns out that if you actually go into the details, we talked about, when I said statistics, we are looking at the number statistics, the photon number statistics. But I can have a similar relation for phase, correct? Phase statistics. So for example, if I take my coherent state, I can say that previously we had plotted n bar versus the histogram of n, right? We got some width of histogram of n. Similarly, I can plot a histogram of phi, right? And then there is some probability of, let's say, n, different photon numbers, or a probability of different phi rather, right? Then I would get some histogram which is like, one block, another block, and so on. I can construct a histogram out of this phase also. Now, what will be the fluctuations in the phase? Delta phi. Okay. So the width of the histogram in this case is going to be delta phi, because the width of your Poisson distribution was delta n. So the width of the phase fluctuations will be delta phi. So the product of delta n and delta phi is greater than, or rather in the coherent state case, it will be half. Okay. Right. Now, if I'm having a phase squeezed light, okay, I'll just represent this by an envelope. Okay, I don't want to show the histogram entirely. I'll show this envelope. So if I have my coherent state envelope like this, if it's my phase and this is my P of phase, probability of certain phase, I'll represent my coherent state by this. Okay, this is coherent. Now what will happen to my phase squeezed light? Okay, in the case of number, the statistics is actually super Poissonian. But in the case of phase squeeze, the delta phi is going to be smaller. So I'll represent it by a straight, narrower distribution like this. Okay, they should be centered in the same. Okay. This is my phase squeeze light.
You cannot define super Poissonian and sub Poissonian for phase.
Well, so far Poissonian we're talking about numbers. So I will have to look at what sort of statistics the phase will exhibit. Okay, and then so basically so always when something is phase squeezed, then it will become amplitude super Poissonian. So it will be basically delta and delta phi. These form an uncertainty pair. Correct. So if you go to amplitude squeeze state, delta n is reducing, so automatically the phase becomes uncertain. This is an important point. So the phase will become something like this. Probability of this phase distribution. This is amplitude squeezed. Okay. So this is how the statistics will change when you talk about squeeze states. All right. You might wonder, okay, in the diagram it is simple enough, but what does it mean physically, right? We understood when we talked about the coherent state. We mentioned that if you have a pure monochromatic wave, you have a single sine wave. But the moment you have a coherent state, I said that it will not be a single sine wave, but there will be a certain width associated with that, right? And that is what I had shown here. Since instead of this, I have drawn it like as a band, right? For example, this will be a band around that, right? Already this is okay. This is basically instead of a line, you have a band wherein that is the fluctuations in the electric field intensity. Okay, but I had drawn always as simply the fluctuations are always constant with time. Okay, that's what I have shown you in the past. That's how a wave will behave. But why does it behave like that? And how does that relate to the circle in the quadrature plot? Okay, for example, think of a coherent state. Okay, so this is a coherent state. This is a coherent state. We know why this is a coherent state, right? Because the region of uncertainty is a circle. And its area, of course, it depends. Minimum area is coherent. Let's say, assume that it's minimum. Okay. Now, what I can do is, this is on the x1 and x2 plot, right? So we know that the x1 quadrature is effectively equal to the electric field. Okay. So now I'll try to take a projection on the x1 axis. So I simply rotate it. In this case, it's x1 is this case. Okay. This is rotated. It's not x2 on the vertical axis, x1 on the vertical axis. So if you take a projection of this state on the x1, this is the region of uncertainty for my electric field, delta E. Now, as it moves on this circle, it will move in a circle, right? Whenever it travels, whenever you have time variation of a wave, we have to the point, the phasor rotates in the quadrature axis. So basically, as you rotate it, how will the projection change? If I, for example, if my phasor or the coherent state comes here, what will be my region of uncertainty in the electric field? It is going to be the projection on the x1 axis, which is this. So the projection on the x1 axis is always constant as I move my the region of uncertainty on that. So as the wave evolves in time, if it's a coherent state, as a wave evolves in time, the region of uncertainty is going to be constant, and that is why I'll represent it as this band here. That's how you can identify a squeeze state. Okay, we'll actually try to, if you take, it should be possible. For example, I'm representing this like, let's say, x1, x2. Okay, and I'm saying that this is my region of uncertainty. So I can think of, in the conventional case, this was basically, this is classical case. I'll say this is, I'll put a point here. I'll put a phasor. This is my classical situation, right? Now, in the quantum situation, I cannot put a single point, but I'm putting a region of uncertainty. So, but effectively, each point represents a particular wave, which can be represented as a sine wave in time, right? Now, if I have these various x1 and x2 components, and I sum up all of them, and of course, each of them is random and there is no relation, so equal probability, equal weightage. If I do it, I should end up with something like this. It looks like this. If I take a circle and I take good enough samples within the region of uncertainty, you'll get this. Okay. So this is a coherent state. What about the squeeze state? Now, if you take a squeeze state, I can talk of, let's say, this same x1 axis, but instead of a circle, I have an ellipse. If I look at this ellipse on the top picture A here, what is it? Is it an amplitude squeeze state or a phase squeeze state? Phase squeeze state, because along the radial direction it is stretching out. In the phi axis it is getting compressed, so it's a phase squeeze state. So if you have such a phase squeeze state here, and it evolves in time, so at time t equal to 0, what is the projection on the x1 axis? It's going to be this much distance. It's a small distance, right? This is the projection on the x1 axis. But after 1/4 of the time period, or of the wave, this is going to the x1 point. What does it mean? This x1 axis, this is the x1 axis and this is the x2, right? Perpendicular direction, I said. Okay. So now projection on the x1 axis is this much small, but once it goes to the perpendicular direction here, after 1/4 of the period, what is the projection on the x1 axis? It's increased, right? This is the projection now. This point is the projection, right? This is projection of the state on x1 at t equal to, I'll just call it as pi by 4. At t equal to pi by 4, that means phase, right? T equal to 0 is 0. So at t equal to pi by 4, you have this. Okay. Now, that means your band of fluctuations in the electric field have increased. Now I'll go further in time. I'll make this state move again to pi by 2, t equal to pi by 2. When I go there, what will happen to my fluctuations on the projection of the fluctuations on the x-axis? Again reduces. So when you go to pi by 2, this is pi by 2, this point, right? At pi by 2, you have narrower variations in the electric field, and continues like that. Again, this is pi by 4, 3 pi by 2. 3 pi by 2, sorry, this should not be pi by, this should be pi by 2, not pi by 4, yeah. Okay, so at 3 pi by 2, you effectively have again large fluctuation, right? You see that, correct? So now, compared to a coherent state, now my fluctuations in the electric field are actually time dependent. Okay? Got it? And what did we say this was? Phase squeezed. What we mean by that is, there are certain time instants where the uncertainty in the phase is actually smaller than the coherent state. Okay. So for example, at these points, here, this and this, okay, uncertainty delta phi is smaller than delta phi coherent. Okay. So that's why we call it phase squeezed. But it doesn't mean that at all time instants the phase is less. It cannot happen. Okay.
you might say, oh, even the amplitude is getting squeezed. Amplitude of the electric field is getting squeezed, right? Amplitude is increasing, reducing. Well, the only thing is how much compared to the coherent state. If you look at the amplitude in this case, I think we'll have to compute. These are, pictures that are taken randomly from various sources actually. I mean, this is from Jerry Knight. It's a very nice book again. So, but you will have to compute. I mean, you can take this sort of a situation, define a region of uncertainty so that the area is, diameters are known, you calculate the area, and from that region you pick up random samples, whatever is there within that. If it falls, then you generate a sine wave out of it. Generate 100 sine waves out of it. Plot all of them. And now make it an ellipse. And then plot all of them. Then we can relatively compare. Okay. So I'm not sure in the textbook what they have taken. This is most likely a schematic illustration, but I think it should be possible to do. Okay. We'll also try to do it and we'll try to post it. Yeah. Okay. So now we can also think of the other scenario where we can talk of the amplitude squeeze state. Okay. This I'll call it as my amplitude squeezed state. Okay. Now, see, always amplitude and phase are not independent. They are interlinked. It's not like, So only thing is, we are trying to compare with the coherent state. So now we call it amplitude squeezed because along the radial direction, the ellipse is narrower. Now if you take the same idea and look at the projections. At t equal to 0, you have large projection on the x1 axis. Right? This is my projection on the x1 axis. But as I change my time at t equal to pi by 2, my projection on the x1 axis is reduced. Again, at t equal to pi, it increases back to this. It keeps going in this. So if I look at my sine wave, the sine wave should evolve with large fluctuations in the electric field. At this point, the amplitude fluctuation is smaller than delta n coherent. That's what we mean by amplitude squeeze state. All right, make sense? So this is a physical meaning. So immediately you can recognize, looking at how the fluctuations in the wave are happening, we can look at. For a coherent state, the fluctuations are always constant with time. But if you have amplitude squeeze or phase squeeze states, the fluctuations change as a function of time. Okay. Now what happens is we can also define one more type of an extreme situation. Okay. The picture on the left is what we have seen many times now. So basically this uncertainty relation delta x1, delta x2 is greater than equal to 1/4. For if it's a coherent, it's equal to 1/4. We also have delta n into delta phi should be greater than equal to half. Right? Now the question is, what happens when delta n is small? Is small. What do we mean by small? Let's make it, delta n is smaller than square root of n. Suppose in any case, what happens? Okay. Now immediately we can see that we know that delta phi is going to be 1 by 2 delta n. Right? Fluctuations is greater than that. No. Phase become now as delta n reduces here, as delta n reduces, delta phi increases. Right? What happens if delta phi is greater than 2 pi? What happens if your delta phi is greater than 2 pi? 2 pi means what? Basically, phase is undefined now. Because your uncertainty in phase itself is 2 pi. And we know that phase always goes from 0 to 2 pi. If you cross 2 pi, again it circles back. You kind of wrap it back into the 0 to 2 pi range. Now if your delta pi itself is large, that means your uncertainty in phase is so large that you can't define a phase. Okay. Now an extreme example of that is what is known as a photon number state. Okay. So photon number state is basically something implies delta n is 0. Can you think of a situation? by delta n equal to 0? Delta n is 0. Delta, the fluctuations in photons is 0. It's not no photons. The fluctuations in the photon number is 0. What sort of scenario will you have that? Perfect subpoisonian light. If I have perfect subpoisonian light, I'll have points like this equally spaced. Okay. Equally, let's say if I have average number of photons, if I make a measurement for 1 second and I find one photon, it's a one photon, average number, photon number state of with 1. If I have 5 photons, it's a photon number state with 5. So basically, it's entirely defined by the number, average number. There's no fluctuation at all. If I have such a scenario, in my case, when I have this state, this is my delta n, right? Radial axis, this is my, radial direction is delta n. Right? Now delta n reduces means what? The phase becomes very uncertain. So now the phase essentially becomes stretched out in this direction. Correct? When the phase becomes stretched out in this direction, so phase is stretched out now. Now what happens if I go to 0? That means I'm essentially defining my state. There's no uncertainty in the number. So this effectively becomes a circle. Radius of circle, and the phase can be anywhere. That's why I'm putting the any circle. If it was the phase uncertainty in the, maybe you can have a kind of a state like this. Okay, you can have a state. Let's say, if suppose one of the ways of imagining this would be this. Instead of this, I'll have uncertainty like this. So the question is, are there any fluctuations in the vacuum state? Vacuum state is pure fluctuations. There are no photons, right? So it's pure fluctuation. What do you mean by fluctuations? Essentially, even in vacuum, it's not like there's no electric field. There is electric field. There's electric field everywhere. Yeah, it's not, it's not uniform. The fluctuations are uniform, more or less it will be flat. Because it's just, some random fluctuations happening, equal probability of all particular things, right? If you look at this vacuum state, if you go back and look at this vacuum state, it is centered at the coordinate axis 0, x1 and x2 plot, it is centered at 0, and you can have many, many different things. You put all of them together, what will you get? Average electric field will be 0. But it doesn't mean that there are no electric field fluctuations, right? There are some fluctuations of electric field. Okay, it's not 0 electric field. Average, maybe, if you take all of them to be equal to 0 over a long time average, okay. But I'll have something there. The fluctuations are there, so there is a non-zero, yeah. Remember what we talked about noise. When we talked about the noise, we said intensity delta I versus delta I square. There is a fluctuations that are there. I mean, if you have no correlations, then on an average it can become 0. But if there are correlations, then it was something different, right? When we talked about intensity interferometers. So now, in contrast to that, we are having a state where here uncertainty in number is reduced. And uncertainty in phase is increased. Correct? That's why it sort of becomes, this stretched out ellipse like this. And eventually, if delta n becomes 0, eventually we can expect that it will become a circle. Okay? So this circle represents the photon number state. What is the radius? Represents photon number. The radius is equal to delta n. Well, I mean, so yeah, we always say that the amplitude is basically alpha and the square root of n, right? But in effect, it should be n plus half. Because half is at 0 point energy. So square root of n plus half. Square root of n plus half is the radius of the circle. So this sort of a situation is called as a photon number state. That means it's completely described by a number of photons. There is no fluctuations in the phase, or rather the phase is completely random. Okay, There's no fluctuations in the photon number. Of course, it's an idealization. Okay. But there are a lot of interesting things about how these single photons are generated. Maybe we'll talk about it later. We'll see. Okay. Is there a scenario where you have perfectly defined phase and completely unknown photon number?
Will that be like not a
So if you want to go to perfectly defined phase, we'll have to go to delta phi is reducing. So delta n has to be large. How much large? It's up to us. So you take a coherent wave, large photon number. You'll have some number. So the delta n will be proportional to its.
So, but delta n will not be.
No, delta n is square root of n bar.
Yes.
If I take a coherent state,
But that will be defined.
delta n is defined, so automatically delta phi will be defined. So you want delta n to blow up. Delta n should be greater than the average photon number. How can that happen? The fluctuations in delta, it can be greater than square root of n bar, average. But you are saying that it has to be infinity compared to that. That I don't suppose, I can't think of a situation where that can happen. Right? Where the phase is perfectly defined, but the number of photons is not at all known. So effectively, it will become a ellipse will be like an going across. Let's say if I think of this is fun. So it should be something like this. Or rather, I can't be two phases. It can be only one side. Sorry. This can be like maybe this ellipse on the let's say one axis. Effectively a straight line. But then no, we have to talk of a region of uncertainty. The length of a straight line again is average, right? Average number of photons. But then that is becoming stretched out.
Length of uncertainty will be in the same direction as the number of. In phase will be.
Compressed. So it will be something like this here, what I'm showing. So it will be like an ellipse which is stretched out, but the phase is in this case some negative phase or whatever, beyond pi by 2 and below 2 pi by 2 pi or pi. You have this. So now what sort of situation will have this? No, I can give an example of number state by fixed average number of photons. All the photons come at the same phase, but then there's an uncertainty whether the photon will come or not. We'll have to, what happens if you have a single photon source? Or rather, single photon source with a very low probability, like, 0.1 photons per pulse or something like that. Like they call it a weak coherent source, weak coherent pulse. But the pulse, whenever the pulse comes, the photon comes effectively. But then most of the times anyway, it's a complicated thing. Yeah. Let's not, we can think about it. Okay. But for now, I just want to emphasize one more point here. If you look at this photon number states, what is the region of uncertainty for that? So what is delta x1? So basically in this case, x1 is, the radius is n plus half, square root of n plus half. Now x1 can vary from this point to this point. From this is my, minus n plus half, right? This is minus n plus half square root. The other side is plus n plus half square root. So my delta x1 in this case would be 2n plus half square root. What will be delta x2? Because it's a circle, that will also be equal to delta x2. So my delta x1 and delta x2 should be equal to 4 times n plus half. So how does this compare? Is it a minimum uncertainty state? What is the minimum uncertainty? Delta x1, delta x2 should be greater than 1/4. But here, even if I put n equal to 0, I am getting an uncertainty of 2. So which is definitely greater than 1/4. So photon number states are not minimum uncertainty states. Right? That's the difference. Coherent states are minimum uncertainty states. Photon number states are not. And as n increases, the uncertainty product is increasing. Okay? But okay? So this is about photon number states. You might wonder and say, why should I care about all this? You know, yeah, I mean, this seemed interesting. You are exploring the limits, but is there any use of this? Okay, I'll give you a use case, which I don't think I also understand fully, but it's an interesting, I'll try to explain to the best of my ability. Okay. So there is a recent experiment which we call as LIGO experiment. So let's try to wrap up, or rather, okay, let me break this lecture here. I'll come back in the next video so that we don't stretch it too much. Okay, so I'll talk about the application of it and how do you measure and detect in the next lecture. All right. So yeah, I think if I make it too long, people will find it hard. Let me stop it here.